A ball thrown upward with initial velocity of v naught equals 20 meters per second from initial height of h naught equals 60 meters follows an equation for its height in meters as a function of time. Y of t equals negative 5t squared plus v naught t plus h naught. Determine the parts A through F. So our position function of time, the height in meters as a function of time, y of t, is negative 5t squared plus v naught, which is a 20 times t, plus an h naught, which is a 60. For part A, we want to determine the velocity as a function of time. The velocity as a function of time is the derivative of the position as a function of time. The first term is a power rule. Bring down the power, multiply with the negative 5. Negative 10, t raised to the subtract 1 from the power. The second term is a constant times t. The derivative will be the constant. The third term is a constant with no t. The derivative is a 0. So our velocity as a function of time is negative 10t plus 20. For part B, we want to find the time when the velocity is 0, and that's found by setting that velocity function of t we just found equal to 0. We can now subtract 20 from both sides, and then divide both sides by a negative 10, and we have negative 20 divided by negative 10, so t is going to come out to a 2. The time units can be seen by looking at v naught here, meters per second. The time units are seconds. For part C, we want to know the maximum height reached. The maximum height is going to occur at the moment in time when the velocity has reached 0, because at that point it's turning around from having headed upward to now heading back downward. So our maximum height will be the height function of t, the y of t, evaluated at the time we just found in part B. The time when the velocity has become a 0 is the time when it's turning around, and we want to know the height when that occurred at, so y of 2. That'll be negative 5 times 2 squared plus 20 times 2 plus 60. So negative 5 times 2 squared is a 4, plus 20 times 2 is a 40, plus a 60. Negative 5 times 4 is a negative 20, plus a 40 plus a 60, which added together would give a plus 100. Negative 20 plus 100 will come out to 80, and that'll be in distance units of meters. Part D, we want to know the time when it reaches the ground. The ground is defined as a height of 0, so we can take the height function of time, negative 5t squared plus 20t plus 60, and set it equal to 0 and solve for the time when this occurs. This has a common factor of negative 5. Factoring that out will give us a t squared, a minus 4t, and a minus 12. We can trinomial factor the t squared minus 4t minus 12 into t and t. We need two numbers that multiply to be a negative 12 and add to be a negative 4. It sounds like a negative 6 and a positive 2 take care of that. So t equals to positive 6 or negative 2. Since times can only be positive, we can ignore the negative 2, and our time for reaching the ground will be the 6 seconds. For part E, we want to know the velocity when it reaches the ground, so we can evaluate the velocity at that time of 6 seconds, b of 6. The velocity function of t we have up at part A. Plugging a 6 in there will give us a negative 10 times 6 plus 20. Negative 10 times 6 is a negative 60 plus a 20. Negative 60 plus 20 is negative 40. And the units will be the distance units of meters per time, meters per second. The negative indicates that it's headed downward when it reaches the ground, which should be the case here. Part F, we want to find the acceleration as a function of time. The acceleration as a function of time is the derivative of the velocity as a function of time, and therefore it will be the second derivative of the position as a function of time. Now we have the velocity function in part A. If we take the derivative of that, the first term is a constant times t. The derivative will be the constant. The second term is constant without a t. The derivative will be a 0. The units for acceleration are the distance units per time squared. So we have a negative 10 meters per second squared.